This is the Busch Microtronic 2090 computer system. In a previous video, I've described how I'm currently working on reverse engineering this machine, and as part of that process, I've developed some really comprehensive notes on everything I've learned about the device so far. Having recently learned about Google's NotebookLM service and the fact that it can take content you've written and convert it into an engaging audio podcast, I thought this would be a great opportunity for us to explore that very long read in a more engaging podcast format. So let's go ahead and start the computer and listen to what Google came up with.
Ready to hit the rewind button on tech history.
Always up for a trip down memory lane.
Today, we're diving into the world of the Busch Microtronic 2090, a vintage West German educational computer. And let me tell you, this thing's a puzzle wrapped in an enigma with a side of mystery.
It's not every day you come across a machine that even its own manufacturer lost track of.
You're telling me?
Yeah.
We've got technical documents, blog posts, forum threads, a whole digital paper trail dedicated to unraveling its secrets. But the real crown jewel, they'd be the monitor ROM.
Ah, yes, the ROM. Vanished into thin air, they thought. Gone for good.
Except a few intrepid digital detectives refused to let it fade away. Talk about a recovery mission.
A real cliffhanger. Imagine this. Arduino boards, voltage levels, these folks were practically reverse engineering on the fly.
Hold on, Arduino boards, like the ones people tinker with today. They use those to wrangle code from a decades-old computer.
Precisely. The Microtronic used a TMS 1600 PMOS chip, mind you. Requires negative voltage, not your usual cup of tea.
Negative voltage sounds electrifyingly dangerous.
You could say that. But these folks, Michael Wessel, Dakeley, they figured it out. Use the Arduino to finesse the voltage just right, coax those secrets out.
Talk about digital delicacy. But data's one thing. Making sense of it, that's another story, right? Like, what'd they find? A jumbled mess of ones and zeros.
More like a symphony played on a scrambled radio dial. See, the Microtronic's program counter, the thing that tells the code what to do and when, it wasn't exactly playing by the usual rules.
Playing hooky with the instruction manual, was it?
You could say that. Jumping around instead of nice, neat order. Some say it was early copy protection, others, a way to squeeze performance out of limited resources. Clever, really.
So how'd they crack the case of the jump in program counter?
With a tool called Nakinism, specifically designed for these vintage chips. It helped them piece together the TMS 1600's instruction set, its own little language.
So they could finally understand what the computer was trying to say. But knowing the words is one thing. How'd they figure out the grammar, the structure?
Time to break out the blueprints. The schematics revealed a crucial connection between something labeled R11 and KL, the key to understanding how the Microtronic talked to its SRAM.
SRAM, that's the short-term memory, right? Like the computer's mental scratch pad.
Precisely. By tracing the connections on the schematic, they could see the code in action, controlling how the Microtronic accessed and manipulated data.
So it's not just reading the code, it's like watching the computer think in real time. What kind of thought processes were they observing?
Well, they noticed that the ROM had a very specific routine for accessing the SRAM. It had to first configure internal registers, sort of like setting the stage.
So before it could even ask for data, it had to get all its ducks in a row. Makes sense. What came next?
Then it would use those registers to store the SRAM address. But there was a hitch. The TMS 1600 could only handle 4 bits of data at a time, and the Microtronic used a 12-bit address space.
That's like trying to cram a whole watermelon into a juice glass. How'd they solve that?
Ingenious workaround. They split the 12-bit address into 3 4-bit chunks, sending each one to the SRAM in sequence, like a carefully choreographed dance of data.
And once it had the data, it could finally... Wait, what was it doing with the data anyway?
That's where it gets really interesting. The ROM would first copy the data into those internal registers we talked about, almost like a temporary holding cell.
Why the extra step?
All because of a single chip, the 4502, a key player in the Microtronic's output system. You see, this chip, for whatever reason, flipped every single bit of data that passed through it.
Talk about a stickler for being contrary.
So the ROM had a whole subroutine just to flip those bits back to their original state, all before sending it along to the rest of the system.
It's like writing a message, encoding it in a secret language, and then decoding it again just so your friend can read it. Seems a tad excessive, doesn't it?
Maybe by today's standards, but that was life in the early days of computing. Working around hardware quirks, finding elegant solutions, that was the name of the game.
They really don't make them like they used to, do they? Last time on our Microtronic adventure, we cracked the code, mapped the signals, basically gave this vintage computer a thorough digital checkup. But did our intrepid explorers stop there?
Oh, they were just getting warmed up. Remember how we talked about recreating the Microtronics brain? They didn't just talk about it, they actually did it.
Wait, they built a computer out of breadboards?
Yep.
Just to test this old ROM? That's hardcore.
Hardcore and then some. Imagine meticulously wiring up an Arduino, connecting it to a breadboard, essentially building a miniature version of the Microtronics core.
So, moment of truth, they flip the switch, and what happens? Fireworks, magic smoke.
Well, the breadboard itself behaved, thankfully. But then, a twist in our tale. Half the keyboard, dead as a doornail, wouldn't respond to a single command.
Oh no, the dreaded silent treatment. Every programmer's worst nightmare, I imagine.
You can say that again. So Barry began the great debugging quest. They checked the connections, combed through the code, even started questioning their own sanity.
It's always good to have a reality check when you're elbow deep in vintage electronics. Where did the trail lead them?
Back to the source of it all. The meticulously recovered ROM. It turns out, the culprit was hiding in plain sight all along.
The ROM itself was sabotaging the keyboard. How's that even possible?
Remember how we talked about the keyboard being laid out like a matrix? Rows and columns, like a digital chessboard?
Right. Activate the right row and column, and boom, you've got your key press.
Well, the ROM was storing the row information incorrectly, effectively disabling half the keys right off the bat.
Like trying to play chopsticks with only one hand tied behind your back?
An apt comparison, and the fix. Almost laughably simple. One single bit flipped from a 0 to a 1, and voila, the keyboard sprang back to life.
Talk about a light bulb moment. It makes you appreciate how much precision went into those early machines. One tiny error, and the whole thing could go haywire.
Absolutely. But the surprises didn't end there. As they continued their testing, they discovered something even more astonishing. The Microtronic was running faster than anyone thought possible.
Hold on, a vintage computer, overclocked. Was it secretly sipping on digital espresso? How'd they figure that one out?
They used their emulator, like a high-tech stethoscope, to listen in on the TMS 1600's heartbeat.
Listening to the rhythm of a 40-year-old chip. That's some serious digital detective work.
By precisely measuring how long it took the chip to switch a specific pin on and off, they could calculate its internal clock speed. And what they found was shocking, to say the least.
Spill the beans. Was it a minor boost or a full-blown need for speed situation?
Let's just say, this vintage machine had some hidden horsepower. They clocked it at a whopping 675 kilohertz. That's 35% faster than the official specs, and even faster than what the chip's manufacturer claimed was possible.
Now that's what I call a blast from the past. Why would they keep such a thing under wraps? Was it a secret weapon in the great 8-bit arms race?
That's the million-dollar question, isn't it? Maybe they wanted to ensure stability. Maybe it was an accidental discovery. Who knows? It just goes to show there's always more than meets the eye when it comes to these vintage machines.
We've uncovered lost code, debugged phantom key presses, even found a hidden turbo boost lurking in this vintage machine. It's been quite a ride. But even with all that, there's one last Microtronic mystery we haven't tackled.
Ah, yes, the one that keeps the truly dedicated up at night. The riddle wrapped in an enigma, shrouded in a byte. 310.
310. Sounds like something you'd find scroll in the margins of a hacker's notebook. What's the story there?
It's the address of a single solitary byte in the Microtronics ROM. And this byte, well, it had a mind of its own.
A byte with an attitude problem. Sounds like my kind of code. What'd it do? Start throwing random numbers around.
That's the thing. Sometimes it was an 11, other times a 10, even a 0 on occasion. Flipping the script, defying
This is
expectations.
the digital equivalent of a magic 8-ball.
Yeah.
Did they ever figure out why he was doing that? Bad connection, cosmic ray interference, gremlins in the system.
They tried everything to pin it down, tweaking voltages, adjusting timings, you name it. But that byte, it just wouldn't cooperate.
So, a true mystery byte. But if it was causing so much trouble, surely it must have been doing something important, right?
That's the strange part. As far as they could tell, the instruction at 3 of 10, it was never actually executed. Not once. Like a phantom limb in the code.
A ghost in the machine. So why even worry about it? If it's not doing anything, what's the harm?
It's the principle. These folks, they were going for a bit-for-bit perfect reconstruction, a pristine snapshot of the past. This rogue byte, it threw a wrench in the works.
I get it. Like finding a misprinted page in a first edition book. It doesn't change the story, but it nags at you.
Exactly. Even with all their efforts, some mysteries just refuse to be solved. It makes you wonder, was it a manufacturing glitch? A tiny flaw in the silicon? Or maybe
Don't leave me hanging.
it was deliberate. A little Easter egg left by the original engineers. A hidden message buried in the code.
Now that's a thought. A digital time capsule just waiting to be cracked. Makes you wonder what other secrets are still out there, hidden in the digital dust.
And that's the beauty of it, isn't it? The thrill of the chase, the quest to understand. Who knows, maybe someone listening right now will be inspired to pick up a soldering iron and embark on their own digital deep dive.
That's what we like to hear. Because as we've learned from the Microtronic 2090, even the smallest of machines can hold the biggest of surprises.
And that's a wrap.
This has been a wild ride through vintage tech, folks. Remember, keep exploring, keep questioning, and most importantly, never stop hitting that rewind button on tech history.
Okay, so I thought that was really pretty good and pretty engaging. Not all of the content is precisely accurate, but if you'd like to learn more about the Microtronic and our efforts to reverse engineer it, do indeed check out my website and do feel free to read through that very long read, the source material for this podcast. And I hope to see you all in the next video.